Okay, chemistry kids, chemistry peeps. Today we're going to be discussing mixed mole calculations. So, kind of using your mole map, if you know what a mole map is, and doing different types of mole conversions, dimensional analysis, mole calculations, molarity, volume of a gas at STP, particles, moles and grams, all right? All types of calculations. We're going to practice them, all right? Now, you need to be able to do this, right? These are types of calculations you need to be able to do. And you need to be able to do them with just a calculator and a periodic table. So if you are, when you first start doing these problems, and we, in honors chemistry, we started doing these problems back in unit 1, okay? You know, if you're using your mole map, that's fine, okay? But you need to start either make sure you have your mole map memorized so that you can reproduce it while you're taking a test from your memory, okay? So you can use it on a test. Or you need to start doing these problems, and the more practice you do, you start weaning yourself off the mole map because you remember what to do. Like if I have mass and I want moles, I divide by molar mass, right? You start to memorize that process. If you need your mole map, then you got to memorize it, all right? So hopefully you start, doing these problems back in unit 1 using your mole map, but as we do more and more of these types of calculations, you start weaning yourself off of that mole map because you just know how to convert moles to particles. I multiply by Avogadro's number, okay? I know how to go from moles of solute to liters of solution. I divide by molarity, okay? So those types of calculations, you need to start just understanding how to do it, all right? So the more practice you do with the mole map, hopefully you start noticing patterns, you start memorizing the different things you do for each type of calculation, and then you don't need your mole map anymore, okay? But if you're gonna always use that mole map, you better memorize it, all right? So let's go to it. All right, let's look at the mole map. So our mole map, we have moles in the middle, and we can go to 4 destinations. If we have moles of a substance, we can go to mass, or mass back to moles. If we have moles of a substance, we can go to particles of that substance. We got to just make sure we know what kind of particle we're trying to get to, right? So is my particle an atom? Okay, is my particle a molecule? Is my particle a formula unit? Is my particle an ion? And we got to make sure the substance that we have to know whatever substance we have, that what we call the smallest unit of that substance, right? So like if I have carbon, which is an element, the smallest unit of that would be an atom, right? But if I have water, a compound, a covalent compound, the smallest unit of water would be a water molecule. I would use the word molecule here. For a salt, for an ionic compound, the smallest particle of that we call a formula unit, okay? So we got to know which type of particle we're going to, all right? Then we have 2 volume locations on our mole map, and we have to distinguish between the two. This is volume of an aqueous solution, so stuff dissolved in water, okay? And molarity is our conversion factor, okay? But if I want volume of a gas, and we have to be at standard temperature and pressure to do this calculation. So when you're told you're at STP, standard temperature and pressure, let that be a reminder that you can use this conversion factor. Okay, so this is only used if you're asked for volume of a gas, all right? But if you're asked for volume of a solution, or you have volume of an aqueous solution, stuff dissolved in water, this is not what we're using. We're using this part of the mole map, okay? So we can always get to moles, and then once we have moles, we can get to whatever part of the map the question's asking about, all right? So let's do some practice. All right, so number 1, calculate the mass of a 5.02 mole sample of chlorine gas. All right, so let's go to the mole map and see what to do. So we want the mass, so we need to end up at mass, and we have moles, right? So we're given moles, so we're starting with that. So if we go to our mole map, it's telling me I have moles and I want to go here. So what do? I multiply by the molar mass. X grams, the molar mass of chlorine in this case, over 1 mole of chlorine, that'll cancel out moles and give me grams. All right. Now, what do we have to remember about chlorine? Aha, it's diatomic. So when I say chlorine, it's Cl2. All right. So I take my moles of Cl2, I calculate the molar mass by looking at the periodic table, 2 chlorines. Each chlorine is 35.45. So I double that, and that's my molar mass. Notice how moles cancel out. I do this times this, and I round to the proper number of significant figures, 3 sig figs in this case, because the moles I had 3. Now, the molar mass I calculated as 4, but the moles I started with only have 3. So my final answer has to round to 3. Okay? All right, let's go to number 2. So number 2. What volume will a 7-mole sample of carbon monoxide gas occupy at STP? So when I see that STP, I'm thinking, oh yeah, I can use 22.4, but I got to know what that means. It means 22.4 liters per 1 mole of gas. That's what STP means. Or 1 mole of gas will equal 22.4 liters at standard temperature and pressure. Okay? So that's just a clue that I can use that conversion factor. But I'm starting with moles again. So I'm starting in the middle of my mole map, and I got to go to volume of a gas at STP, right? That's what we're looking for. So if we look at our mole map, I'm starting here, and I want to get to here. And to go from moles, I follow that arrow, and it says use that conversion factor, 22.4 liters over 1 mole. So let's see how the setup looks. So I take my 7 moles of carbon monoxide, CO, and I multiply by that ratio. Moles cancel out, and I'm left with liters. Both the molar volume, 22.4 liters, that has 3 sig figs, and the 7 has 3 sig figs, so I got to round my final answer to 3. And there we go. All right. So let's go to the next one. All right. So a sample of nitrogen gas, they remind us that nitrogen is diatomic, so that's nice, has a volume of 95 liters at standard temperature and pressure. So we're at volume of a gas at STP. So that's where we're starting on our mole map. And we need to figure out the mass. So we're starting at liters of a gas at STP, and we need to get to mass. So again, let's go back to our mole map and see what we have to do. We're starting here, and we need to get to here. So it tells us to multiply by this ratio, 1 over 22.4. So what is that really telling us to do? Divide by 22.4. And then, again, we're going to use this one to go from moles to grams. We're multiplying by the molar mass. All right, so let's see how that sets up. All right, so we would start with our 95 liters of nitrogen gas, divide by 22.4 liters per mole, so liters cancel out, and now we have moles on top. So right now, if I do 95 divided by 22.4, now I would have moles of nitrogen N2. And now to go from moles of nitrogen to grams, I multiply by the molar mass. So again, I find this, 1 nitrogen is 14.01, so 2 of them is 28.02. So now moles cancel out, and I'm left with grams. So again, I would divide by this and multiply by that. It doesn't matter what order you do. You could do 95 times 28.02 divided by 22.4. It doesn't matter what order, but you're multiplying on top, you're dividing by the numbers on the bottom. You can kind of ignore the ones because it doesn't change your value if you multiply by 1 or divide by 1. But let's 3 sig figs, 3 sig figs, 4 sig figs, so I'm limited to 3. So that would be 119 grams, if you want to be more specific, 119 grams of nitrogen, N2. Okay, so let's go to number 4. All right, so I have 6 liters of a 0.65 capital M, that means molarity, and the way we read that is we have a 0.65 molar solution of sodium chloride. So now we have an aqueous solution, right? So now we're not looking at the volume of a gas at STP, we're looking at the volume of a aqueous solution. Okay, and we want to know how many moles of the salt. So we want to get to moles, and we have liters of a solution. And that's what we're starting with. So let's go to our mole map and see what we're doing. We have liters of a solution, that's where we're starting, and we want to get to moles. So we multiply by the molarity, right? Molarity is our conversion factor. So remember, whenever you see that capital M means moles per liter, moles of the solute per liter of solution. So that's how molarity is a conversion factor. And whatever the molarity number is, that's the X moles of solute per 1 liter of solution. So let's set this one up. Whoops. Okay. So we would start with our 6 liters of our solution, and we would use the molarity as a conversion factor, right? That's how we translate this measurement, 0.65 capital M. Really, it's moles per 1 liter. So that many moles of the solute. In this case, the solute is sodium chloride. So liters would cancel out, and if we just do liters times molarity, that gives us moles. I know in my classes, I always say our mantra for molarity is liters times molarity equals moles. Say that to yourself 1,000 times and just remember it, because a lot of times that's what you have to do. Liters times molarity equals moles. Liters times molarity equals moles, right? So that would be moles of sodium chloride, all right? So let's go to the next one. So we're starting at the same position. If you notice number 5, we're starting at 6 liters and we got the same concentration of solution of sodium chloride, but now they want the mass. So if we go to our mole map, right, we're starting here again. We're gonna multiply by the molarity to get to moles, and then we gotta multiply by the molar mass to get grams of salt. All right, so we're gonna multiply by the molarity, and we're gonna then multiply by the molar mass of the solute. In this case, the solute is sodium chloride. All right, so let's see how that looks. So again, I start with my liters. I use my molarity as a conversion factor to cancel out liters and get moles. And then how do I go from moles of something to grams? I multiply by its molar mass. So this 58.44 is just the molar mass of sodium chloride. Sodium is 22.99 on your periodic table. You can look it up, right? And chloride is 35.45. So we add those up and we get 58.44. So we multiply by that ratio, moles cancel out, and you're left with grams. Now notice here, our liters had 3 sig figs, our molar mass had 4, but notice the molarity only had 2. So that's why I rounded my final answer here to 2. And the same thing up here, I had to finish with 2 significant figures because the molarity measurement I had only had 2. Remember, leading zeros, never significant, all right? All right, let's go to number 6. All right, number 6. A student requires 25 grams of HF. So we have 25 grams of HF, right? So we're starting at mass. And we want to know what volume of a 0.85 molar solution. So this is not a gas. This is an aqueous solution, right? Let molarity be the key there. So we're looking for volume of a solution, not volume of a gas at STP. So if we go to our mole map, right? Hold on, sorry. If we go to our mole map, we're starting here and we want to finish volume, but remember it's volume of a solution, so we need to go here. We're not going down here. It wasn't a gas, all right? So we're here, we got 25 grams of HF, if you recall. Now, to go from mass to moles, what do? We divide by the molar mass, 1 mole on top, the molar mass of HF on the bottom. And then to go from moles to volume of solution, we're gonna divide by the molarity, right? If we multiply going this way, that means we divide going the opposite way. So to go from volume of a solution to moles of solute, we multiply by molarity. To go from moles of a solute to liters of solution, we divide by the molarity, all right? So we're going to divide by the molar mass, and then we're gonna divide by the molarity. And that'll get us there, all right? So let's see how that works. So we start with our 25 grams of HF. We have to calculate the molar mass of HF. Hydrogen's 1.01 and fluorine, 1 fluorine is 19. So 20.01. So grams would cancel out. And then this is how we convert our molarity unit to a conversion factor that cancels out moles and gives us liters, right? The way we should interpret this is 0.85 moles of this per 1 liter, but we can flip that ratio and say 1 liter of this solution for every 0.5 moles of this solute. So we flip that ratio, moles of HF cancel out, and we're left with liters. And we should go 3 sig figs because we had 3 sig figs here, our molarity was 3 sig figs, our molar mass was 3 sig figs. Now, technically, I should put like 1.000 here to maintain significant figures, but you get the gist, okay? And then let's go to the last one. All right, so it is found that a 30-liter solution of ethanol contains this many molecules of that alcohol, of of ethanol, and we want to know the molarity. So remember, molarity. So in this question, we're not ending up at one of our destinations, okay, in the mole map. So we have volume of the solution, and we have how many particles of the solute we have. And we want to find the molarity. So notice, what I want you to notice on your mole map is molarity is not a destination on our mole map, right? Right? Molarity is a conversion factor that we use to go from one place on our mole map to another place. So we have particles, okay? And we can get particles to moles, but to get moles to molarity, we just divide by the volume of solution, right? Molarity is moles of solute per liter of solution. So you could use your molarity equation if you wanted to and say, okay, molarity equals moles over liters, plug in your 30 liters, and now you just have to figure out moles. But you could just do it in one-dimensional analysis setup. So we have molecules, so we have particles. So going back to our mole map, we have molecules, and we got to get to moles. So what do? We divide by Avogadro's number, and that'll give us moles of the ethanol. All right, so let's see how that looks on a setup here. Okay, so we would take our molecules of the compound, we would divide by Avogadro's number, that would give us moles. And if we just remember, capital M molarity is moles per liter. Right now, just doing this divided by that gives me moles on top. So how do I get moles per liter? I divide by liters. So all we have to do is take our moles. So after we do that, that'll be our moles. And then we divide by the 30 liters. And what would we have left? Molecules would cancel out. And we would have moles on top, liters on the bottom. That is moles per liter. So we get 0.346. And you could have capital M. And a lot of times that's how you kind of see molarity most of the time. But if you want to, the better way to interpret that, capital M, is moles per liter. Moles/liters, okay? All right? So if you can do those calculations, if you understand what we were doing there, then you're in great shape. If not, you need to figure it out. How do you figure it out? You go get extra help, okay? You come in and you practice. It's just not, it's not going away. We're gonna be doing mole calculations the rest of the year. When we get to Unit 6, it just goes up another notch. All right, so you were warned in Unit 1, the sooner you understand dimensional analysis, the better, okay? So if you're still not there yet, we gotta get there. We gotta get there. Dimensional analysis is not going away, okay? So keep practicing. And if you need help, you need to come before school, you need to come after school, you need to come get that help. All right, but most of the time it just takes practice. It just takes practice, and once you get it, you get it. But if you're not willing to put in the time and you think it's just going to magically come to you, well, you're not going to be as successful as you want to be. All right, so hopefully this helps. Have a great one.